In this lecture, I will be talking about abstract algebra and different concepts that are involved. This includes automorphisms, homomorphisms, isomorphisms, kernels, groups, fields, rings, the Gauss lemma, Eisenstein's criterion, and Kalwa theory. We will not be covering all of Kalwa theory, as that is very advanced, and it involves concepts that are not included here. However, we will be covering a decent amount about the rest of the topics. So, I will be starting with the three first ones, automorphisms, homomorphisms, and isomorphisms. A homomorphism could be related to a function in some way. One could say that a homomorphism is a function between two sets. For example, we could say that the set 0, 1, the set even and odd numbers could be homomorphic to the set 0, 1, which would be the set of integers modulo 2. This set is really important, and as it is one of the sets of the integers modulo of prime number. Also, it is important to notice that this set is a field. Also, the set of even and odd numbers is also a field, which means that we can take something notice. A homomorphism preserves most of the characteristics of a given set. For example, it preserves all of the field actions that it follows. In other words, if you have a set that is a field, it is all of its homomorphisms will be a field. Also, we have isomorphisms and automorphisms. These are other types of functions between two sets. Isomorphisms and automorphisms are both injective. However, isomorphisms are bijective, whereas they both have a difference in the range. This means that an automorphism is slightly different to an isomorphism. Generally, in abstract algebra, we deal with isomorphisms and homomorphisms. We rarely deal with automorphisms. However, they're sometimes used. Okay, so that's all about these three topics. Now I'll be covering the three algebraic structures, which are groups, field, and rings. There are also semi-rings, which are really similar but have some differences. For example, the natural numbers would be a semi-ring, whereas the integers are a ring. So the following, all of the algebraic structures follow some axioms. Axioms are the rules that they must follow in all circumstances. Some are stronger, whereas others are weaker. A field is one of the strongest algebraic structures that exist. That means that they follow more axioms than other algebraic structures. So these are the field axioms. The addition field actions are the following. When adding two numbers in a field, you will always get another number in that field. It will never go outside of the field. This is called closed under addition, which is really important, as this means that sets like that are not closed under addition are not fields, which is really important for the definition of a field. The next axioms for addition states that addition is commutative. In other words, if you add two numbers in that field, you will get the same as adding it the other way around. For example, if you add x plus y, you will get y plus x. Also, they must be associative. In other words, when adding three numbers, it doesn't matter if you add the two first than if you add the two second. In other words, x plus y plus z is the same as x plus y and then plus z as y plus z and then plus x. They also have an identity. The additive identity is generally 0. However, they can be other things. The characteristic of the additive identity is that when adding a number to that identity, you get the same number. We also have inverse. A number plus its inverse equals 0, and an inverse plus that number equals 0, which can be derived from the commutativity. You also have the distributivity. If you add a number, we also distributivity, which is a mix of addition and multiplication, which I'll mention later. Then for multiplication, we have the same things. For example, close on the multiplication, commutative, associative, and inverses, which is very similar. However, the identity is a little bit different. A number multiplied by an identity gives the same number. However, there's an important rule about this. The additive identity cannot be equal to the multiplicative identity. Else, it is not a field. There is a very important field that doesn't follow this.
If I can interrupt, could you explain that point about the multiplicative identity, like you told some special rule?
Okay, so imagine the 0 set, which would be a very basic set with only one element, which I'll explain what's so important about the fact that it only has one element. So the 0 set has the same addition identity as multiplication identity, because 0 plus 0 is 0 and 0 times 0 is 0. However, the problem with this is that the rules, the axioms say that the additive identity are not allowed to be the multiplicative identity. So this means that a set can have a minimum of 2 elements, as one of them has to be the additive identity and the other one the multiplication identity. This is represented with 1 is not equal to 0. Does that answer your question?
Wait, I didn't get it. How did that go to 1 is not equal to 0? Like the
the number 1 generally represents the multiplicative identity, and 0 represents the additive identity. Which is why I said 1. Okay, so those are the field actions. Another thing that is in the actions is the distributivity property. A multiplied by B plus C equals A times B plus A times C, which is really obvious, but it's important, which is common in all fields. Okay, so in case that you have not figured this out, a field also must have two operations, addition and multiplication. Just adding this fact in case you didn't. Then we have groups. Groups are slightly different than fields, however, they're also one of the main structures for abstract algebra. They also follow some important axioms which are important to be known. The thing about groups is that they are not generally as famous because they don't follow some of the axioms that fields do. These are the axioms of a group, the group axiom. First, it must be closed, like fields. It must be associative. In other words, x plus y plus z must be equal to x plus y and then plus z, or x plus y plus z first and then x. Okay, so that those are the first two, and then we've got that it must have an identity such as 1 or 0, and it must have an inverse. The most important thing about this, which is what you should remember about groups, is that they don't have commutativity. They may have it, but it's not necessary, and that they have one operation, but they don't need to have two. So they could have only addition, only multiplication, or some other weirder operation that is not as famous. For example, rotation would be a valid operation in case of shapes. Okay, then we've got the ring, which is another algebraic structure which is not as strong as a field. Rings also follow some axioms, and as I stated before, they are an integer, for example, would be a ring, and the integers would be a ring. However, the natural numbers would not be a ring. It is important to notice that the natural numbers are a semi-ring, which is a and this course is a very easy way to remember that, and there is a very easy way to remember that natural numbers are a semi-ring. Natural numbers are, funny enough, half of the integers. This means that they are a semi, and that is a trait that is explained in a few books of algebra. A ring.
Wait, Neo, if I can interrupt you, could you explain how the integers are a ring and natural numbers are not a ring just once more?
Okay, so these one of the I'm going to explain first what the ring actions are, and then I will answer the question because it's important to know these actions. The actions are: it must be abelian, in other words, it must be commutative under addition, which means that the associative property is followed, the commutative property is followed.
Right before this, you told about a group, and you told about the group does need commutativity, and is a ring a special kind of group?
No, a ring is a separate structure which is not related to the group.
Mm-hmm. So what does it consist of? It's a set.
It's a set that is abelian. In other words, it's associative, it's commutative, it has an additive identity, which is 0, and it has an additive inverse. However, the natural numbers do not have additive inverses, right? Because there's no negative numbers.
Oh, yeah, there's no negatives. Yeah.
Which means that the natural cannot be a ring. Then it is a monoid for multiplication, and a monoid basically means that multiplication is associative and that there is a multiplicative identity that for which 1 is not equal to 0, which I explained before for the fields. That means that there is at least 2 elements, and so this means that the zero group is not the zero set is not a ring. Multiplication is also distributive with respect to addition, which means that that I explained before for the ring, for the field. For example, a times b plus c equals a times b plus a times c, which is basically the definition of distributivity. Okay, so those are the basic algebraic structures. Now I'm going to be talking about kernels. Kernels are kernel, first of all, is German for nucleus, and it is related to someone to a nucleus because one could say that the nucleus of a group of any algebraic structure is the identity. So to work out the kernel, you would have to so to work out the kernel of any given set or group, you would have to work out what operations you have to do to get to the identity. So I'm gonna give an example because this explanation was a little bit too hard in my opinion. So let's see, I have a homomorphism from the integers from a group of 2 integers to a group of integers, and let this homomorphism be from, for example, a to a plus b. So, for example, imagine I get 2 integers, 3 and 5, for example, Applying this homomorphism, I get the integer 8 because I do 3 plus 5, which gives me 8, which is a homomorphism I just decided to define. This means that 3 and 5 are members of the kernel of the homomorphism. If and only if the kernel of if the homomorphism of A and B equals 0. This means that A and B are members of the kernel of a homomorphism if and only if their addition is 0 for this homomorphism. So for the homomorphism I just made up, the kernel would be the set of numbers such that A plus B equals 0. This means that that A and B are in the kernel of the homomorphism if and only if B is the additive inverse of A. For A, and I repeat, this only happens for this homomorphism I just made up. So this means that the kernel of the homomorphism would be A and minus A, where A is an integer. Kernels are slightly more complicated, and the main idea of explaining what they were was so that you have a basic idea, and that way you understand a little bit about how they work. Now I am going to be moving on to Kalwa Theory, and in Kalwa Theory I am going to explain a few things. So in Kalwa Theory we've got the Gauss lemma, Eisenstein's criterion, and the different hypotheses about the Kalwa Theory. So the Gauss lemma, I'm not going to explain it really deeply. I'm just going to explain that it exists and what the basic idea behind it is, as it's a little bit complicated and it's way above the expectations of this lecture. So the Gauss lemma has the idea of the same idea as the Eisenstein's criterion, which is to show that a polynomial is irreducible. For a polynomial to be reducible over a group, it means that you cannot work out the answer to the values of the polynomial, the values of x in that polynomial in that group. So let's give an example: x squared plus x plus 1, where x is a real number. Here we've got no solutions to this in the real numbers, and you can use the quadratic formula if you do not believe me. However, you'll find out that x is a complex number, or more precisely an imaginary number, and thus this means that x squared plus x plus 1 is irreducible over the reals. So the Gauss lemma has the basic idea of showing this. However, it's a little bit more complicated than the one I'm going to explain. The one I'm going to explain. Yes.
If I may interrupt you, why did you say where the polynomial is irreducible in a group, like rather than SL?
Well, yes, unfortunately, I should have said that in a set. However, basically, you'll be mostly dealing with groups when doing Kalwa theory. But yeah, I should have said in a set if I wanted to be completely correct.
Yeah.
Okay, so now I'm going to move on to the Eisenstein's criterion. And these are the main characteristics of the Eisenstein's criterion. So suppose I have some polynomial, and there are 3 conditions must apply for it to be indivisible. For it to not be for it to be irreducible. We have so imagine a polynomial is of the form an times x to the n plus n minus 1 times x to the n minus 1 and so on. So you need to find a prime number.
Could you write this down? I didn't quite follow.
Okay, yeah, I can write it down. So imagine I have some polynomial a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 and all the way like that. So if I had that such polynomial of that type, and there are three conditions that must apply. So first of all, you must find a prime number which divides all of the coefficients except for the coefficient of the biggest degree term. So, for example, if I give you the polynomial, if I give you, for example, the polynomial 3x to the n, 3x squared plus 4x plus 1, you would or I'm gonna give a better example in this case, plus 2. So you will have to find a prime number which divides a prime number that divides 4 and 2, but not 3. Because
two, right?
What?
Oh, okay, sorry. The answer is 2, right?
So you'll have to find a prime number which divides 4 and 2, but not 3, because that's basically the Eisenstein's criterion. So it must the prime number must divide all the terms, all the coefficients except the coefficient of the largest term. Okay, the next rule is that it must not divide the largest term, which I basically just stated. And finally, that the square of that prime number that you find must not divide the smallest the coefficient of the non-existing of the constant term. So in the case of the example I just gave, 3x squared plus 4x plus 2, we can test this. So the prime numbers, we could try the first prime number, 2, and we could see that 2 divides 2. 2 is a factor of 2, 2 is a factor of 4, and 2 is not a factor of 3. Thus, it follows the first two conditions of the Eisenstein's criterion. Now we would do 2 squared, which is 4, and 4 is greater than 2, so it definitely cannot be a factor of 2. Thus, we conclude that 3x squared plus 4x plus 2 is irreducible over the reals. Now, if you do not trust me, which given the fact that you've not studied so much the Eisenstein's criterion, it's possible, you can test it out. You could find out the discriminant of the quadratic formula. B squared is 16, and you can work it out, and you will notice that it has no real roots. Because the discriminant of the quadratic formula would be the square root of 16 minus minus 24, which is the square root of minus 8, which is obviously incomputable over the reals. Okay, so this is one of the examples, but we could get even harder examples. Imagine I gave you this polynomial, which would be x squared plus x plus 1, which was the one I gave you at the beginning. Here, there are no prime numbers we could test, which might suggest that it is reducible over the reals. However, it's not. We would have to make a substitution, and we could write it as f of x equals x squared plus x plus 1, and then substitute x equals x plus 3, and do f of x plus 3 equals x plus 3 squared plus x plus 3 plus 1, and evaluating that, which would give us x squared plus 6x plus 9 plus x plus 3 plus 1, which would be x squared plus 7x plus 13. And in this case, x plus 3 might not have been the best substitution. So we could test another substitution, maybe x plus 2, and see if that one works. So x plus 2 squared plus x plus x plus 2 plus 1, which would we could test and do x squared plus 4x plus 4 plus x plus 2 plus 1, which would give us x squared plus 5x plus 7. And this is one of the problems with Eisenstein's criterion. I have to go on lots of times with different substitutions until I find one that satisfies the Eisenstein's criterion. For this reason, people generally prefer the Gauss lemma.